All right, 41. Explain why any substance's heat of fusion is generally lower than its heat of vaporization. All right, heat of fusion is the heat required to melt something. Heat of vaporization is the heat required to vaporize something. So when you're vaporizing something, you are pulling it apart, right? You're breaking the intermolecular attractions that hold the solid together. Whereas when you're melting something, you're just disrupting the crystal, right? You're rearranging the crystal. So heat of vaporization is always higher, recognizing that, hey, if this is the heat I got to put in to vaporize something, the heat I'd have to take out to condense something would be the same magnitude but opposite in sign. So whereas heat of vaporization, heat of fusion are endothermic, heat of condensation, heat of freezing would be exothermic. All right, ethanol melts at negative 114 degrees Celsius and boils at 78 degrees Celsius. The enthalpy of fusion of ethanol is 5.02 kilojoules per mole. Its enthalpy of vaporization is 38.56 kilojoules per mole. The specific heats of ethanol are 0.97 joules per gram per Kelvin and 2.3 joules per gram per Kelvin for being in the liquid phase versus the solid phase. Okay. So, how much heat is required to convert 42 grams of ethanol at 35 degrees Celsius to the vapor phase at 78 degrees Celsius? All right, so in order to do this problem, we introduce this thing called the heating curve. A heating curve plots heat energy put in to temperature increase. So when I heat up a solid, right, heat put in, I speed the molecules up, right, the molecules move faster, and the temperature goes up until I hit melting. When I melt something, the heat doesn't go towards increasing the temperature anymore. It goes towards pulling the crystal apart. Once it's melted, once it's in the liquid phase, now we can increase the temperature again, right? So you're putting heat in and the temperature goes up, right? Molecules moving faster, faster, faster until we get to the boiling point. At this point, the heat is going in to vaporize the substance, but it's not going towards increasing the temperature until we vaporized it. Once you're in the gas phase, then heat can go towards speeding the particles up again. So a heating curve. This is graphically how it works out. Notice how the heat of fusion line is shorter than the heat of vaporization line, right? It takes more heat to vaporize than to melt. So using this, we have different heats. First heat we're dealing with is heating up the liquid until we get to the vaporization point, right? From 35 degrees Celsius to 78 degrees Celsius. So anytime we're dealing with the relationship between heat and temperature, it's Q is equal to NC delta T, right? This equates temperature change to heat change. So the N is the mass of the ethanol we're heating up. C is how hard it is to heat up the liquid ethanol. And delta T, change in temp. So Q1 is the heat required to increase the temperature of the ethanol up to the boiling point. So Q1. Put it in kilojoules. Q2 would be the heat required to get into the gas phase. All right, so that's what they wanted. They wanted to get into the gas phase. So in order to do that, we want to use the heat of vaporization, all right, which is in kilojoules per mole. If I multiply it by moles, I can convert to how many kilojoules is required, right? So do I have a mole of ethanol when I have 42 grams? No, not quite. All right, so less than a mole. So I'm not going to need the full 38.56 kilojoules in order to convert from moles of ethanol to kilojoules. So it's going to be less. I don't have a mole, right? A mole would require 38.64. I have less than a mole, so it only requires 35.2 kilojoules to raise the temperature of that mass of ethanol. So that's Q2. So if I want the whole total heat change, Hess's law says it just add them together. So Q1 plus Q2 gives me the heat change required. All right, so that was for A. For B, how much heat is required to convert the same amount of ethanol from down the solid phase, right, negative 55 degrees Celsius, to the vapor phase at 78 degrees Celsius. All right, so this is a longer trek. We'd need to know how hard it is to heat up the solid, right, the heat capacity of the solid, and the temperature change. So I'm going from 155 kilojoules, 155 degrees Celsius to 114 degrees Celsius, right? The point where I start to melt ethanol. So Q is equal to NC delta T. What I need to know is how hard it is to heat up solid ethanol. All right, so they gave me that. I needed how much ethanol, and I need to know the temperature change to get Q1. All right, so that's the heat required to heat up the solid up until it's going to melt. Now I need to know how much heat is required to melt, right? So it's the same as the last problem, right? I need to know how many moles of substance I have multiplied by the heat of fusion in kilojoules per mole. So I use the molar mass of ethanol to convert to moles, use the heat of fusion to convert from moles to kilojoules. All right, so I have less than a mole, so again, it's going to take less than 5.02 kilojoules to melt ethanol, this amount of ethanol. Then I want to heat all the way from the solid phase up to the liquid phase, right? So that's going from negative 114 degrees Celsius to 78 degrees Celsius. This is Q3. Q3, I'm utilizing Q is equal to NC delta T. Again, the specific heat of the liquid ethanol times the temperature change times grams gives me how much heat's required to increase the temperature from freezing point up to boiling point. Put it in kilojoules. And then I want to melt it. And this is it, right? I'm only going up until melting, right? So I need to know how many moles of ethanol I have and multiply it by the heat of vaporization to get it into kilojoules. So Q1, Q2, Q3, Q4. Add them all together to get the total heat. And this is how I do it. All right, put a little star on this one. Definitely something you have to be able to do. The fluorocarbon compound C2Cl3, F3 has a normal boiling point of 47.6 degrees Celsius. The specific heats of the liquid and the gas are 0.91 joules per gram per Kelvin, 0.67 joules per gram per Kelvin, respectively. The heat of vaporization for the compound is 27.49 kilojoules per mole. Calculate the heat required to convert 35 grams of this fluorocarbon from the liquid phase at 10 degrees Celsius to the gas phase at 105 degrees Celsius. All right, so we're using this curve again, right? We're starting at 10 degrees Celsius and going up to the boiling point. So I get a delta T. We have a way of equating delta T to heat. I need to know how hard it is to heat up the liquid, multiply it by how many grams I have, and the temperature change, and I can get the heat change, or heat requirement, in order to go from 10 degrees Celsius to 47.6 degrees Celsius. All right, now calculate the heat required to convert go from the liquid phase to the gas phase, right? So this is using heat of vaporization. So for Q2, I need to know how many moles of substance I have. Multiply moles by kilojoules per mole, right? The heat of vaporization in order to convert to kilojoules. So I have way less than a mole, right? So I have way less than the 27.49 kilojoules required to convert this amount to kilojoules. So this is Q2, 5.13 kilojoules required. Now, heating up a gas also requires heat, right? And there's a heat capacity for the gas. So multiply the heat capacity by the amount of gas, right? 35 grams. By the temperature change, you're going from 47.6 all the way up to 105 degrees, right? This is how hot you're getting the gas. And plug it into Q is equal to NC delta T and solve for the heat. So Q1 plus Q2 plus Q3 is going to give me the total heat. So that's how much heat's required to raise the temperature of this substance that amount. Explain how each of the following affects vapor pressure of a liquid. So first thing before we start answering these, we have to remind ourselves what vapor pressure is, right? So anytime you have a liquid, a certain number of the particles in the liquid have enough kinetic energy to escape the liquid phase and go into the gas phase. And this is what vapor pressure is, right? It's the pressure of the particles in the gas phase over the liquid. So in terms of what's going to affect this vapor pressure, volume of the liquid? No, it has no effect. There's no, a little bit of volume, a lot of volume. You can have the same vapor pressure at a particular temperature. So surface area won't have an effect. Big surface area, little surface area, you're still going to have the same amount of pressure sitting up over the liquid. Intermolecular forces. Now this has an effect. All right, so stronger intermolecular attractions holds those particles back and won't allow them to go into the gas phase. Temperature, so like I said, right, it's temperature dependent. Higher temperature, right, the particles moving faster, they're going to ignore intermolecular attractions and go into the gas phase easier. Density of the liquid, right, heavy particles are harder to put into the gas phase than lighter particles. So high density, lower vapor pressure. True or false? Tetrabromomethane is more volatile, meaning it's easier to put into the gas phase than tetrachloromethane. No, that's a no, right? Because you have stronger intermolecular attractions between bromine's more polarizable, so you can get greater dispersion forces with bromine than you will with chlorine. And it's heavier, right? So it's harder to put into the gas phase. So volatile means how easy you are to put into the gas phase. Volatile substances are easy to put into the gas phase. So tetrabromomethane would be less volatile. Therefore, it would be harder to put in the gas phase, so it would have a higher boiling point. Stronger attraction is harder to put in the gas phase. Weaker intermolecular forces. No, stronger, right? This is why it has a higher boiling point. More polarizable, and it's more polarizable. Has a higher vapor pressure at the same temperature. No, it has a lower vapor pressure, right? So lower vapor pressure because it's heavier, and you get more induced dipole attractions.